So let's start our portion of complex analysis. What we do. Uh, I have little small things that I want to talk about before I do anything, which is about convergence of a sequence of complex numbers or a series of complex. You probably know them very well. Even then, okay, if I have a sequence of complex numbers, okay, a sequence of complex numbers uh, is converged with earlier, but anyway, one more time converged. Now, if I have a limit, okay, if I have a uh, L in C such that A and converges to L is what I want to say. So that means the difference between A and L can be made as small as possible as N gets bigger, such that for every epsilon greater than 0, such that the distance between A and L is for all N. So after such a state, the name will be very small. That's when you say A converges to L. Okay, it's a pretty easy thing. Everybody knows. Now, if I have a series of complex numbers, not just a sequence, but their sums, okay? A series, you mean this comma A K equal to 1 to A N equal to 0 to infinity or 1 to infinity. Okay, starting point. Of complex numbers, okay, are said to converge. Yeah, is said to converge. Well, if the sequence I want to use A naught plus C, A1, A2, and so on. Forever, that forever has to go to some. Yes. Okay. I will say that provided if you look at the partial sums, A naught plus A1, A naught plus A1 plus A2, and so on, you look at A naught plus A1 plus A the partial sums. Sn is the partial sums. Okay. If this C the partial sums tends to S, tends to S, I think this sample is the best. Okay. If of partial sums is Sn. What is Sn? Sn is the sigma A equal to 0 to n. Sum up to the first n. Okay. Converse. Okay. If that converges, you can say that getting bigger and bigger, bigger. It's taking some quantity, and that some quantity is the infinite sum. Okay. If Sn converges to S, as n tends to infinity, we say sigma n equal to 0 to infinity converges to S, and its sum is F. Okay. We have already seen that the space of complex numbers is complete. That means, because first of all, any convergent sequence is Cauchy. So on account of that, but there is a converse also. Space of complex numbers is complete. That means every Cauchy sequence converges. So convergence is equivalent to Cauchy. So therefore, sigma n equal to 0 to infinity converges if and only if the partial sum sequence is Cauchy. That means n and m are getting bigger and bigger, and the difference between Sn and Sm will be as small as possible. So now there is a large number. Is less than epsilon all m and 10. Yeah. Okay. That is actually small. Okay. That is actually difference between Sn minus Sn. Small. Okay. So if it cannot take A1, etc., up to AN, suppose M is bigger than M, and then AM, and then go on to AN. The whole thing is SN, and this is SM. So from SM, if I from SM, SM is up to M, is up to N, what remains is the remaining is here. Okay, so this is actually the difference. Sn minus Sn minus 1 is less than 1. Okay, then rather than equal to M, then capital. Okay, so this is not too much. I just said what I mean by series converges. Okay, a series converges provided its partial sums converge, which is equal to saying that in this series, if I look at the order of such a stage and then go on for a little distance, I don't get too much. I get something small. So for every zero, there's a large enough n such that the difference between the partial sum from m to n, that is sigma ak m equal to a from m to n, is less than epsilon than omega equal to n. Okay, this is just what you learn in your calculus. What I will also say is that absolute convergence. Okay. If the absolute values of the if sigma mod a n equal to 0 to converges, we say sigma a n equal to 0 to infinity converges absolutely. Absolutely. Absolute convergence, absolutely. So absolute convergence means sigma an is said to be absolutely convergent if sigma mod an converges. This is of course mod n is the modulus of the complex number. These are non-negative real numbers. So this series of real numbers, while this is series of complex numbers, these complex numbers are said to convert. If this series of real numbers converges, actually absolute convergence will actually imply convergence of the series. We can first yes, that. So absolute convergence usual convergence. So here's a little theorem. We say that, okay, if sigma n equal to 0 to infinity converges absolutely, then it converges. Then absolute convergence implies convergence. That's not a very big thing. It's can be easily seen. See, what I'm going to do is do a little bit of reflection, convergence of the series, and then convergence of power series, and later we will eventually show that we want to talk about analytic functions. Uh, functions in some sense differentiable neighborhoods of a point are analytic functions. We will show that every power series expansion gives you an analytic function, and every analytic function gives you a power series expansion. Okay. Once we're done with that, then we'll talk about analytic functions and the properties of the analytic function. It has very rich, theory behind it. Analytic functions actually very nice in the sense a lot of control is there in the values of the energy function. So we'll talk about all those things once we go through this process. Talk about what power series is and why power series are differentiable and the derivatives can be calculated, and then introduce analytic functions and show how analytic functions are representable as a power series expansion. So power anything that is representable in the form of a power series is analytic vice versa. So we will first get over this, and then we start real complex function theory about the theory of analytic functions. So anyway, converges, absolutely converges. You can prove that easily. Let's say you want to look at the sequence of the partial sums. You want to say that the sequence of the partial sums are going to converge, right? Yeah. Let Sn be sigma ak at k equal to 0 to n. This is the sequence of partial sums of ak. I want to show that this actually converges, right? What you're given is this convergence, okay? So let epsilon be greater than, okay? Since sigma mod n equal to 0 to infinity converges, because that converges, I have the property I have just talked about. For this epsilon greater than 0, such that sigma mod k equal to n, in modulus is less than epsilon for maybe n greater than equal to m greater than equal to n. Therefore, if you look at Sn minus Sm, which is really sigma ak k equal to m to n, this is the usual partial function. You look at Sn minus ms is sigma ak equal to m to n, and you're going to look at a modulus of that. And but that is less than equal to sigma mod ak k equal to m to n. But you say this is less than epsilon for m n greater than equal to m greater than capital N. Okay, which means you approve, and therefore it has convergence that finishes the part. Therefore, Sn is Cauchy. A Cauchy sequence in complex in the complex plane should converge because complex plane is complete. Completeness of a metric space is actually means that a topological space X is said to be complete if every position converges. And we proved that the complex Sn is Cauchy in C, hence. So I proved you absolute convergence implies convergence. Any questions so far? Everybody okay? I'm going to do the next. Well, we talk about sequence of functions. This is also probably done already for. Anyway, here is a little theorem I want to say, maybe a definition first. Suppose X D is a metric space. Okay? XD be a metric space. And look at the sequence of functions. Fn is a function from X to C. So this is a sequence of complex value functions. Okay? And F is X to C. You can say uniformly. Okay, we say Fn converges to F uniformly because this is the functions, right? Functions depend. Function depend. For example, if I take a small x and capital X, and I look at Fn of X, that is going to be just a sequence of complex numbers. And well, when talking the sequence of complex numbers, converges or not. That is not just point-wise convergence. So we can say Fnx converges to Fx. That's point-wise convergence. Okay. So what I want is I want that point-wise convergence means I can find for all
The voice is breaking very badly now. This voice is breaking very badly. Now we can, at least I can't hear. Well, maybe it's on my side.
I will see to that somebody. Okay. Yeah. Okay, I will tell me if it is fine now.
Yeah, it's okay now. Yeah, let's.
So you see, this Fn is a sequence of functions and x. So for each x in x, Fn x is a sequence of complex numbers. Okay. So the sequence of the complex numbers converges or not, we can talk about. Suppose I want to say that this complex converges. This convergence is going to depend on x. Okay. So this then depends on x. If you change x sequence, that's a different sequence. So this is going to depend on x such that the bond Fnx minus Fx is less than epsilon for all n greater than equal to capital N. So this capital N depends on x. But if I can do this for every x, and the first of n is chosen irrespective of what the x is, then I say this convergence is uniform. There is a point-wise convergence. So this convergence for each x in x this convergence is saying that the whole convergence we have informed. We want to talk about it. Do we say Fn converges to X? Okay. If for every epsilon greater than 0, there exists a capital N, a positive integer, which is not going to depend on any particular x. I'm going to do it for every x and x. There is a positive integer N in Z such that the mod fnx is less than epsilon for all n greater than equal to n and for all x in x. Okay. So for that epsilon, I have one single capital N beyond which the rest of it, which x it is, fnx minus fx is less than epsilon. I hope you understand. We have, I think, discussed a little bit of it already, so that when we did this before, I just want to make sure I have it here.
That's right.
Okay. we write in this case that Fn produces to F as n tends to infinity to say Fn converges to F. Next. Okay. Now, let me introduce what is called the power series. Let's say I have a sequence of complex numbers. An are all complex numbers. For An in complex numbers for all n, okay, I'm going to look at the series. The series sigma An some not n in order to see what it will be. In other words, from this A naught plus A1 Z minus Z naught plus A2 Z minus Z naught whole squared and goes on forever is power about Z is called power series. About Z naught or centered at Z? About Z. Centered at Z. Okay? Most power series 0 only, then that looks like some n equal to 0. Okay. In particular, course in particular, course is centered at Z naught. The centered at 0 is this. Okay. This is your A naught plus A1Z plus A2. Because it's going to depend on the complex number Z. So it's a series of functions. Okay. Oh, I should have done one more small thing. Excuse me. I will go back. I have to discuss one more small thing. Please allow me. I need a research so that I can. This is the waste class test. We need to do that. Waste class test. About the convergence of a series of functions. Suppose I have a series of functions, Fn x2. Again, I can even talk about a Okay. Let u n equal to u be a function from x to c. Uh, the series sigma to n equal to 0 to infinity. These are this is series connects. Okay, uh, is set to converge uniform on x if the series of functions converge uniformly. Okay, if sigma the series if the sequence Sn, which is actually sigma k equal to 0 to n, functions of sigma into n. Okay, uniformly on x. Okay. The first system converges uniformly. Then I say this series converges uniformly. Okay, we're talking not about this sequence of a series of complex numbers, but we are talking about series of functions of complex numbers. And the series of functions of complex numbers converge uniformly. With portions of series of functions converge uniformly. Okay. So we have what is called Weierstrass test. For a moment, I think my understanding of the Weierstrass spelling is Weierstrass. Weierstrass is one instrument in developing the concepts of analysis very systematically. The epsilon delta arguments must have come from Weierstrass. They were using some, you know, crude sentences to explain those things, but the argument involving the fundamental types of things actually started with Weierstrass. Weierstrass is a really great analyst who wanted to do everything extremely rigorously. Anyway, Weierstrass is a very simple test, nothing big deal. I have a sequence of, let's say, let u be a function from x to r. There exists some mn greater than 0, such that mod unx is less than equal to mn for all x in x. Okay, so this series is dominated by the series sigma mn. That's what each un is dominated by mn. The theorem says sigma mn converges. Sigma mn is a sequence of a series of positive real numbers. If that series of positive real numbers converge, then the series of functions will converge uniformly. If sigma mn n equal to I can start 0 to infinity converges, then this is sequence of real numbers convergence plus the sequence of functions converge uniformly. On X. Sir, is that all right, sir? You understand the statement of there? It's called Weierstrass test. So sometimes the convergence series of functions can be very easily very easily concluded if we can find a dominating series sigma mn of positive real numbers. This converges, then that has to come. Okay. But if some of them become kind of unbounded, as n goes to infinity, they get bigger and bigger. I may have convergence, but I don't get this test. Proof. Am I fine with that, sir? Proof. Very easy, sir. I just look at the convergence of sigma mn to the point. Okay. Okay. I have a series of sigma to small right? So I'm going to the series of the sequence of partial sums. Maybe UK k equal to 0 to n. This is for Sn. I have to show that Sn converges uniformly to some s. So let's do for each n a natural number, let Sn be sigma 2k k equal to n. So Sn is a function now. Okay? Sn is a function. It is for every x, x is sigma 2kx. Okay? I want to show that this sequence is going to be Cauchy something. Let epsilon be greater than 0. This is actually, this is the, let this be the of partial sums. Okay. A sequence of partial sums is the sequence of partial sums of sigma n equal to 0 to 3. Okay. First of all, the way I will show you that simply x and x, Sx is Cauchy. Once I say Snx is Cauchy, and Snx is Cauchy in what? Cauchy in C, and therefore Snx has to transfer some Sx as n tends to infinity. But then I show you that this is not just point, it is actually good. I finish the problem. Okay. So let epsilon be greater than 0. Since sigma mn n equal to 0 to infinity converges, there is a large enough n such that that sigma mk equal to m to n is less than epsilon for all of them. I can put epsilon by 2. I can do that epsilon by 2 for all n greater than equal to m greater than equal to n. Okay. Now Sn minus Sm, Snx minus Smx, okay, in modulus is really the partial sums separated, right? So this is nothing but sigma ukx k equal to m to n. I've taken n to be bigger than m, okay? And that is less than equal to sigma k equal to m to n mod kx. But irrespective of that, this is the less equal to sigma mk k equal to m to n. I don't need modulus here also. But there are series of real numbers. I even this modulus there. There is no need of modulus. Is that right? I just write it like that. K equal to m to n. Okay? And that's what it is. This is less than epsilon by 2. Therefore, this answer would have been there, leave it. Therefore, you see that this is Cauchy sequence. Okay. Therefore, for each x and x, what this is for all n greater than equal to m greater than or equal to n, and for all x, and for all x. So for each x in x, sequence n x is Cauchy. The complex image the images of complex numbers, right? So it's Cauchy in C, and therefore it converges. Okay, it converges. Do some x in the complex. Okay. So I said SNX converges. Let's go back to this one more time. So I have here, so what is that? SNX converges to SX, right? SNX converges to SX as n tends to infinity. This happens for each x and x. Of course, this point of convergence only. Now we have to show the uniform convergence. Now, this particular step I have, I can call this some one or something. Okay, one implies. Now, if you let, for example, n tend to infinity, leaving m as it is, okay, this modulus is always less than epsilon by 2. Therefore, as n tends to infinity, the limit is also less than epsilon by 2. Okay, sx minus sx. So that is taking limit as tends to infinity. Bracket taking limit as n tends to infinity. We can obtain the following, that mod this becomes sx minus smx. That is smx minus epsilon less than epsilon 2. That is less than greater than or equal to. And there is nothing about x. It's true for every x. For every x. Okay, no matter what x I took, working out. So I just finished it. Therefore, convergence is uniform. This is true for every x. Okay. So therefore, the convergence is okay. This is true for every x. Yeah, I had shown like epsilon gives 0. I'm able to find a capital N so that mod smx minus sx less than epsilon for all m greater than n and for all x in x, which means that convergence is uniform. Therefore, Sn S as n tends to x. So this test is quite convenient. Okay? This is a series of functions, but they are bounded. Each function is bounded, right? Each unx is bounded by mn. Yeah. Okay. I'll go back to the previous page. So what is that? Un is a sequence of functions, and there is an mn that said unx is less than mn for all x and x. So each un is bounded by mn, but these bounds, which are dominating the series un, themselves are going to be convergent. So we have a dominating convergent series for this series. For this series of functions, I have a dominating convergent series of real numbers, and this dominating convergence, now dominating the series is converging, then the sigma un has to converge uniformly on x. Is it clear, sir? Any questions so far, please?
I'm just trying to rephrase this. So if you have a series of functions un, and if they're all bounded by a set of mn's, And if that series is converges, then you're basically saying that this thing is converging to uniformly. Yeah, it makes sense. That's and to
Making
prove
sense.
that we're okay.
Yeah, making sense is quite convenient. The ULs are maybe very bad, but they're dominated by a convergent series of real numbers. And so they should. Okay, everybody.
Yeah, yeah. Yes.
Very soon I will talk about power series. Very soon I'm going to talk about power series. Power series is going to depend on uh, many complex numbers in the domain of the power series. And so I have to talk about convergence of them is to talk about in terms of uniform convergence and everything. Then the Weierstrass convergence will be quite useful.
The power series will basically just become a special case now, essentially, of Weierstrass. Yeah.
I think this proof is okay, sir.
Yeah, yeah.
So you see, the topology is being used very nicely. I only showed the SL X in the Cauchy frequency, and the frequency is complete, it converges to something. And then when I use the same one, in which I let L tend to infinity, if L tends to infinity, this goes to Sx minus epsilon. At best, it will become less than infinity epsilon by 2. Might encroach epsilon by 2.
Yeah.
But then there is less. That's what. Okay. Next. I'm just going to introduce a small concept, nothing much in this. Given a sequence AN of complex numbers, of real numbers, we will introduce what is called limit supremum. Supremum makes sense. Supremum is like, yeah, it is a bound because it could every one of them. And it's the smallest possible bound. That means if you take anything less than that bound, some of them will pass there. Okay, first term supreme. One means it's a number m. N is less than m for all n. And if I take anything, this is the least upper bound. That's what is least upper bound. If I go below m, some of the ends will cross. So for every epsilon where there is 0, there exists a maximum to cross. There exists a small one n in natural number such that an crosses m minus epsilon. So supremum means least upper bound. This is also a notation least upper bound. Okay. Maybe I should define that also then. Okay, supremum. I'll talk about supremum. Define supremum or least upper bound of an. If you allow infinity, then that's supremum or least upper bound an is m. An is less than or equal to m for all n in Z plus. I'm going to allow m to infinity also in my next definition. Okay, supremum can be infinity. N less than or equal to m for all n begins n in Z plus, and for every m less than r less than m. Oh, I go slightly to the left. So the infinity is r is a finding point. For every r less than m, there is n plus. So that okay, r is less than Yeah. Okay, so M is the smallest, the least upper bound is an upper bound because it's bigger than every one of them. But that's the least upper bound because if I go below M, anywhere, some of them will cross. Now, this definition works even if M is infinity. In this definition doesn't work if M is infinity because M minus epsilon doesn't make sense. Okay, so I decided to be a definition where infinity, M can be infinity too. Is that clear to you, sir? It's the least upper bound, and the least amongst the upper bound. So, in the sense that if you go even below that, okay, then some of the ends will cross. Okay, and similarly, infimum. Or infimum lower bound, and the greatest among the lower bounds are the greatest lower bound. Okay, okay. I have to give you some other name. Is okay. When if L is less than equal to AN for all N in J plus, and why is it the greatest lower bound? If I go bigger than that, some of the N's will come down. And every R in so that one AN that it's not beyond right? Is R. So that R cannot be assumed to the greatest lower bound. Okay, nothing beyond L can be a lower bound because some things will be below R. Okay, this is the definition. So the this L can be minus infinity also. Okay, M can be infinity too. Okay, can be infinity. L is minus infinity are also possible in my definition. Okay, sir. Then I'm going to define what is called, limit supremum. Limit supremum as tends to infinity of an. Okay. I'm not looking for the count of all the an's because initially there may be some big numbers, but afterwards the numbers may mellow down. So the initial few numbers should not really disturb the concept of the supremum. If I want that, I want to discount the first few numbers which may be very big. After that, they go down. Okay, so limit supremum is the following. I look at the supremum, AK, greater than equal to n, and then the limit as so if there's some unnecessary debate, you can forget about it. Eventually, that is the least upper bound. And that's what limits to. I'll explain that. And similarly, limit infimum. Of A is looking at the infimum of AK beyond N, but then it's more as an exponent. Okay. We want to understand this a little bit. Instantly, I will denote this also by the symbol limit supremum as L tends to infinity A. And this I write it limit infimum as L tends to infinity. Okay. There is also a notation. Okay. I want you to feel comfortable with my definition. I can make an observation to give you a feel of what I'm talking about. I'm talking about the supremum. Let's call this is M. Okay. Suppose this number is M. Okay. So uh, for every number, okay, right? What happens? This limit is going to be R is greater than M, and therefore, incidentally, you notice that this is to come from N onwards. Then the next one is to come from N plus 1 onwards. Then the supremum is from N plus 1. So
So,
this supremum is decreasing sequence. This is a
in any
decreasing
case,
sequence.
supremum AN,
Subramanian, you were saying something.
can it be unique in any case? Supremum
Ah,
AN, can
yes.
it be?
It is. It is unique.
Because we
Yeah.
are talking about limit, in some cases it may be unique also, no? So supremum AN.
See, that's what happens. First, you notice that supremum is the decreasing sequence of M. This is an expression involving N, right? It's Sn. Sn is decreasing because I'm looking from AN plus 1, AN plus 2, and so on. And the next one I am looking at AN plus 1, AN plus 2, and so on. So you have to give the supremum for less number of elements. So the supremum I get here is less than the supremum I get. Perhaps maybe AN is a bigger one amongst all of them. The supremum for this one is N, but the rest of the supremum will not be smaller than. So this is the decreasing sequence. The sequence of real numbers, okay, and they're all bounded by many boundaries. So you see that decreasing sequence of numbers, okay. First to understand that, and so so that is R and on the other hand, for every okay, remember may cross uh, uh, this M also, okay. There is okay. This can cross M. If cross here, there are some of them can cross this M. Many things cross, but eventually the limit will be this. Limit of this, another representation is less than gamma, but I could say that everything is less than M. Something more than M. Whereas if I look at it on the left hand side, then I see that because the limit is this, many things will have to cross this gamma. In fact, things have to cross this gamma. Okay. So, there is a subsequence. This is that see, what is happening is limit supremum is following. You can take this, for example, I can take two numbers. I can take, 40, 30, 200, 7, 1, right? 1 by 2, 1 by 3, 1 by 4, etc. Okay? The supremum of one of this is 40, but you need to do the behavior. Okay? So they are not, as if you look at this, yeah, there is one. But if you look at supremum from half, there is half. But if you look at supremum from one side, there is one side. The limit is 2. 0 is the limit supremum of sequence. Is that clear?
You're breaking up, but the limit an, the series an, does that have to be a convergible series? We're not saying anything.
No need. I don't.
For any
I don't
series,
need.
for any sequence an.
Okay.
If it is an oscillating sequence of right, so like a sinusoidal or something, take something like that. Now the supremum is in many places, right?
No,
every peak will become a.
No, I look at 1 by 2, 1 by 3, 4, 1 by 4, 1 by 5, that is 1 by 2, plus 1 by 2, 1 plus 1 by 3, 2 plus 1 by 3, we take this sequence. Start going between 1 and 2. But supremum is actually going to be 2. Limit supremum is going to be 2. Because if I go on and after such a stage, look at the limit. Look at the supremum. Supremum will be 2 plus 1 by n. And as n tends to infinity, it goes to 2. So limit supremum of that is 2. Okay? I'm ignoring a few things in the middle. Actually, I'm ignoring all big things in the middle. Eventually, what is that? It is stabilizing 2. And amongst them, which is the, in some sense, greatest. So least upper half is what the limit supremum. There is a difference between just the supremum and the limit supremum. I hope you understood that.
Yeah, supremum is the global supremum, a global max, basically, right? In this case. Yeah.
Where the limit supremum is like, I don't want a few things in the beginning to disturb that. If you really look at the sequence, the supremum is 40. But really, the numbers are not near 40, they're somewhere else. So I don't want this 40 to dominate the business. Okay, I don't want the 200 to dominate. But little go further, the 200 and all the things are little trash compared to the tendency of other objects. Okay.
So if I take that first sequence that you put 40, 30, 200, 7, 1 half, 1/3, 1/4, and so on, the limit supremum is 0 and the limit infimum is also 0 in that case. essentially.
Yes, 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 liquid exists.
Yeah.
Actually, if the liquid exists, then limit supremum and infimum will both be same. Suppose
If
you have
limit
two
exists,
subsequential.
yes. Yeah.
Suppose you
That's
have two subsequential limits.
right.
One limit goes to this, one limit goes to that. The smaller one is the limit infimum, the bigger one is the limit supremum. Okay.
Sir,
Go ahead,
can you
please.
hear?
I
Yeah,
think I
so
missed that.
so this limit supremum is like placing an additional term at the end of the sequence, like a limit point, which is not actually in the sequence. Before that term, every term there exists some terms in the sequence. So not actually
Maybe.
numerical value, not actually.
Okay, actually, sequence is there. Sequence is there. For example, I have a sequence like 1 minus 1 by 2. Okay, 1 minus 1 by 3. 1, 1 minus 1 by 4. 1, if I really depends, this problem is 1.
Yes.
Because 1 is coming forever. Okay, whereas this 40, 30, 200 are coming in the beginning and they don't come back again. Okay.
Yeah.
Every now and then, if 40 games cover forever, the limit supplement will become 40.
Yes.
That's I'll explain that. Okay, in the example. I just used the definition, but spend time on this. So, supremum is the maximum and the least upper bound. So it is above everything and is the least upper bound in the sense that anything smaller than that is not an upper bound. That means some of them will cross that quantity. Anything smaller than that, some of them will cross that. That is the least upper bound. Okay, which is what I call supreme. Limits means you look at subsequential limits and they supreme. That's what it is. You calculate supreme on the first few and then take limit as enter screen limit. Okay, so as such, if your supreme is m, if I cross m, okay, so m is here. If I cross this, because this increasing sequence towards that, once you cross all the whereas if I go on this side, maybe R is here, there may be people just coming in for some time and going away, sometimes going away. That's, okay, that's not important. Okay, but whole lot of things will be okay. So infinitely many things come inside that. That is why this is not the if only infinitely many things come inside that, all of them will come below that. I want that. I want many things come beyond R. So I cannot say and do is the least for bound. That's I think these two sentences are very interesting. Okay, so I have done a little note. So what is the note here itself? So supreme as n tends to infinity of the okay. For every new r there exists such that if p is less than something beyond that is less than r. Whereas for every r less than m, maybe I will use the same symbol. I put R1 this, R2 this. Okay, R2 plus N, there exists a subsequence A and K of A such that A and K is greater than R2. Okay. Okay, it's not a limit supermom, because some things can go on that, but not forever. Okay. Since some things will cross. Because this is not supermom, because okay, so if everything, if there is no subsequent classes, suppose all of them are you know, below that, they don't ask this. So that you don't want. That's why. So I can only infinitely class R2. That is why it is not the limits. Okay. Don't worry. We are just one.
So there may be series where you won't find any limit supremum.
Infinity will be limits supremum then. Infinity.
So if I take a simple sin x, whatever it is, sinusoidal sequence, right? The supremum will be 1. Since it is oscillating forever, so there is no n beyond which I can say that it is settling down, right? So what is the limit supremum there?
Which sequence? For which sequence?
A sequence of sinusoidal values, sin x.
Okay, sin x. Okay.
Yeah, just sin
Yeah,
x.
sin x.
Yeah.
Yes. Okay. Sin 1, other sin x. Okay. Let's say this. Yeah.
Right.
1 is the limit.
1 is the supremum. Yes, sure. But what is the limit supremum for that? Because it has to be the same thing. Yeah. Because at some point of time I can prove. Yeah. Okay.
1 is the limit supremum. Once again. Yes. Once again. You strike something very interesting there. What is happening is you have to take a limit. Instead of saying x, I have to say maybe some n, right?
Right. N. That's what I mean.
And this is less than equal to 1 for all n, okay? Okay. But if you really look at, so you see what you're looking, this is the limit supremum. What are you taking? Supremum of a k greater than equal to n, and you're looking at the limit of that. Okay. Of course, it's a little because sine 1, sine 2, sine 3, sine 4, they keep oscillating.
Yeah.
I think it's supremum, and then you bring the limit. So it's the limit supremum. Okay.
Yeah. Yeah, you take all the partial subsequences and take the supremum of that and the limit of that. So you can naturally say 1 will be there at some point of time, and that becomes your thing. Okay.
I will taking a little risk, but I think one should because sine n is to watch carefully. Yeah. Okay. I don't think we should need to worry too much about this particular thing. I use it slightly, not much. Okay. In my discussion, I use it very little. Yeah, maybe I should pose some questions. I will send you some questions. You can think about those things. Okay. Now, power C is in C. series of the form. Sigma n z minus z naught raised to n three. Okay, is not a force is here this is equals to complex numbers. Okay, let an be a complex number for all n. It is called a power series. I can say centered at Z naught or about Z naught. I mean, not considered at Z naught. In particular, I can have the power series centered at 0. In particular, sigma n z raised to n and infinity. Okay, actually, what is this? This is plus a1z plus a2 squared, etc. Is power series centered at 0. I want to understand whether this power series converges or not. I think Mistra's test will very quickly tell you a very easy way to say whether the series converges or not. Okay. You have some standard series, 1 by 1 minus z, for example, is easy. For example, I will talk about more later. Anyway, for example, take 1 plus z plus z squared cube, etc., etc., straight power n, which is actually 1 by n and as one, if one z for n plus 1 will tend to 0 as n goes to infinity, and therefore you say what z infinity term, the will is okay, you have examples. So what I want to know is how do we decide whether such a power series converges or not? Well, it turns out if these coefficients are, we'll see them. So I want to write it about convergence here. Okay. Funny. Once. For a given power series, sigma an z minus naught zero to three. Okay. Capital R. Capital R can be 0 and infinity. Okay. By what? By the following. 1 by capital R is limit supremum as n tends to infinity of mod an to the power of 1 by n. Okay. Supremum as n tends to infinity of mod an over 1 by n. Okay, I will define this number. Then I can add the reciprocal of that. Right? So in case there is 0 or is infinity. In case the reciprocal is infinite, r equals 0. I am allowing that also. Anyway, this mod by n power 1 by n, everything is non-negative. And so the limit can be 0 or infinity. If it is 0, r is infinity. If it is infinity, r is 0. I want that. Okay, then A. If z naught is less than capital R, the series converges. The series is sigma n converges. Bounded frequency. Indeed, the terms of the series are bounded. And I will do one more thing. See, if 0 less than r less than r, I go even little lower, then the series, then the series converges uniformly. Uniformly on set of also. Okay, right? So not only, so what is that? With respect to every person is given like that, there is a data, and there is a certain radius like that. Okay, this is convergence is uniform. That's what I'm saying. So the radius of convergence, or called radius of convergence of this. There is a circle beyond which it diverges below, inside which is about on the rim. This says nothing about on mod z minus z equal to r. How convergence actually is uniform. On the entire mod z minus z not less than r, the convergence is there, point-wise convergence. But if it goes slightly low, then the convergence on the entire this is what I'm not actually some of these series I may also at some points in the boundary. I did not converges on the boundary. Some trees converge at some places and some places don't converge. I want to prove this thing. I don't know how much time remaining. I the proof of this and maybe I should achieve something. So if you guys allow me, another 15 minutes, we'll just First of all, I think I would rather assume that not withdraw because the same proof follows everywhere. Instead of saying margin pen is not is less than this and so on, it just they say margin is less than or something. So let's assume they're not each zero. And you can see whatever proof I write works through even if the series is centered at some other point statement. Okay, so let's first assume that they're not equal. Okay, any questions about this?
I think the last one, C, wasn't clear for me. You were breaking up there very badly. So what we're saying is if I take a small r less than r, then the sequence, the series converges uniformly on the ball of XR. That's what we're saying.
So, yeah. Okay. And that the convergence is uniform. Uniform convergence is very much necessary for it doing a lot of things. Okay. Inside, if it goes like the convergence is uniform. The convergence is uniform. Okay.
Okay.
Look at the convergence is there. Inside outside ball of various has diverges. So it's also I have a little circle drawn around. I can't go beyond that. Inside I'm okay.
Yeah.
Space. So as I said, I'm going to assume Z0 is 0. Whatever I prove I write is going to work out even if Z0 is 0. Okay. I want to show convergence inside I want to prove the first game, which is convergence inside disk of radius r centered at 0. Okay, so take a z inside this ball of radius r. Okay, so mod z is less than r. Okay, is mod z is less than r. I can actually squeeze in some mod z. Okay, choose small r so that mod z is less than r less than capital R. R is okay. Therefore, 1 by r is less than 1 by r. What is this r? R is the 1 by r is the limit supremum. 1 by r is limit of mod n for 1 by n. And I have taken a number beyond that. I have taken a number beyond that. So I think limit should go to this r, and therefore it will be less than 1 by r. So, right, then there exists a positive integer so that all quantities an mod for 1 by n has to be less than 1 by r for all n greater than equal to capital. Okay, is that right? So if you look at mod n to n, I'm going to apply Visa's M test here. If I look at this, this is actually mod an into mod z raised to n, but mod an is less than 1 by r for n. So this is less than mod z by r. Okay. But mod z by r is less than 1. It's quantity less than 1. Okay. Therefore, the sigma mod z by r for n, that's when it converts. And since mod z by r is less than 1 greater than 0, sigma mod z by n by r n equal to, sorry, mod z by 1 r power n equal to 1 to infinity, 0 to infinity, no problem, 0 to infinity, converges. Therefore, Divister's interest is therefore by interest sigma am, therefore n equal to 0 to infinity, converges. Okay, sir. Now I want to solve the actually I have simplified convergence inside. I will prove the C immediately. I proved A, right? This proves A. I will prove C directly. Why not? Now I'm gonna do that. Let 0 be less than R, less than R. I want to show that inside the disk of radius R, the convergence is uniform. Okay. Choose another number row between these two things, so that R is less than R. Okay. Now what happened? This therefore 1 by R is less than 1 by rho. Is less than 1 by R. Huh?
Right.
Yeah. Once again, I have the same thing. I think there exists a capital N in Z plus such that mod an power 1 by n is less than 1 by rho for all individual capital N. Is that right? Which is mod 1 by an is less than 1 by rho 1. Okay. Now just go ahead and do this. Therefore, mod an z power n equal to mod an into mod z power n, but mod an is less than 1 by rho power n into mod z power n, which is mod z by rho n. So what happens? Therefore, for every this is like if you mod if I mod rho, so this is less than what is that? Mod is less than R, right? R by rho over n for every mod z less than R. Okay, so I say this for mod z less than R, you have the result. But now it's not doing a z anymore. This is just a this is a well, let me go back. I said something wrong here. There is no need of Vestas and there is no need of Vestas and just convert this. Point wise, right? Is that right? It's just convert this. It's going to depend on Z also. Whereas now in the next phase, now this is not depending on Z anymore. I can call this MN. Okay? Sigma R by rho over n, n equal to 0 to infinity. Look at R by rho is less than 1 and positive. And now I think that is dominated by this. Okay, so now you apply waste assumption, and you say that this series converges uniform. Is that okay? Now, not that you cannot use waste assumption in the previous one, but that is not going to say anything. It only says point waste convergence. Now, by waste test, okay, sigma an z for n. Why this converges? Since 0 less than r by rho less than 1. Okay, waste test. Sigma a and z for n equal to 0 to infinity converges uniformly. B0 R. Look at this. And that is your R. I have dominated by a sequence of real numbers which are converging, and therefore this converges. Okay. Actually, if I just took margin to be close to R, I will not be able to do this. It's because I took margin to be less than R, and I am able to squeeze in one more in the between. I am able to manage this. At least as far as the proof is concerned. Okay.
Yeah, if small r is capital R, then you can't use that R by that convergence and call it as an Mn. Like R by rho to the power of n. That series, you cannot say that it will be converging.
I think the last thing is now very easy. The same way I get inequality reverse, I'm going to get the inequality reverse, and I get this number will also be this time. I take this number, which is important one. I will just for this number. So I think I'll give you the last proof now. Finally, to prove, so this proof C. At the end of the story, I just want to know some results. Then we understand what the theory is going on. Proof is very much necessary, but beyond the proof, I need to remember what is the result happening. That's quite useful for us. Okay, fine. To prove B. Where is the Z? I'm going to take the Z will be taken outside. Let mod Z be. I'm going to squeeze in some number between the two things. Okay, so choose small r. So that mod Z is greater than small r is greater than. Okay. Now again 1 by r is less than 1 by r, and this is the limit supremum mod n for 1 by n. Okay, now you see that therefore infinitely many times the an for 1 by n will be crossing this. So there exists a sequence, subsequence. Are there is infinitely many? There exists infinitely many n. So that, okay, this an mod an, its limit supremum is 1 by r. So 1 by small r is not limit supremum. So lots of things will cross and go towards 1 by r. So this is 1 by r. Okay, greater than 1 by r. So now let's start with mod an z raised to n is mod an into mod z raised to n. Mod z is greater than small r. Okay, and mod an is greater than 1 by, yeah, okay. So yeah, mod an is greater than 1 by r. So mod z by r raised to n. And but mod z by r is greater, this quantity is greater than 1. And so this summation is going to be a divergent, and this is dominated by those terms, infinitely many of those terms which are tending to infinity. This is tending to infinity as infinity. Why? Since mod z by r is greater than 1. I think that tells me, this series cannot it is diverse. Terms are becoming infinite. Therefore, sigma an z for n equal to 0 to infinity diverges. Okay, so let's just summarize what we did. Corresponding to a power series, okay, centered at Z0, I will be able to find a disk around it. Okay, I'll be able to find a disk around it of the radius r is something. Actually, the radius r is called radius of convergence of the power series. So that outside this disk of radius r centered Z0, the series diverges, inside it converges. But if you go a little bit more inside, that means we take a compact cell inside that. Okay, maybe a small, little bit going inside that, and the convergence is uniform. Okay, this is what we prove, and this number r is called the radius of convergence. So here is the definition. The number r above is called the radius of convergence of the power series. The radius of convergence of the power series. Sigma an z minus z raised to n by 2 a. Okay, I think I'll stop here. What I will do is a little later on, I'll send you a few exercises. You can try to find out the radius of convergences of some of those power things. With this an z minus z raised to n equal to 0 to infinity, which is actually plus a1 z minus z naught plus so introduce r to be the maximum as n to infinity of mod an power 1 by n. Okay. Actually, there is another simple way of writing this radius of convergence. We'll do that also. Another convenient way of writing the radius of convergence. I'll do that. I think very soon, you might read already in the textbook. The immediate result of that is, in case an by an plus 1, modulus of this, the limit of this as the n tends to infinity exists. In case this limit exists,
Yes.
quite similar derive that. That is very nice. Actually, finding the radius of convergence from this formula is easy compared to the finding it from this. Okay, I will send you why in our textbook itself, in the first exercise, there are some questions he asked, asking the radius of convergence of 2 or 3 series. Okay, I will read it from the textbook. On page 30, he has exercises. Okay? 6 exercises about exercise 6 is giving you about 3 or 4 series, and he's asking what is the radius convergence of them. And 7 is also very instructive exercise. You try exercises number 6. Sir, any questions so far?
One question I have is, we haven't talked about what happens exactly on the radius of convergence.
Yes. So I have examples to give you. Nothing happens. You cannot really say anything. There are series I can give you. Some of them converge at few places on the boundary, and they do not converge at few other places on the boundary. Actually, catch hold of a function which does not converge at every point on it. is going to be a very interesting thing to do. Okay? Right? I give you examples of many functions which converge in few places on it, and maybe at all places on it also.
Okay.
I don't know whether I give you that example or not. I can give you input for that also. But finding, power series which do not converge at any point on it is also very important. I will give you eventually an example tonight because we're not got into that. What I was telling you is later on, immediately after this, we start analytic functions. A function which is differentiable in a neighborhood of Z0 is said to be analytic at Z0. Later on, we prove that any function which is analytic at Z0 will actually admit a power series expansion like that. So, and on the other hand, even before that, we prove that any power series expansion, of course, is after all a function. It is a function. And wherever it converges, and there is a zero r, it is a function. And we prove that this function is analytic, and conversely, any analytic function has to admit such a power series expansion. So, what are analytic functions? Precisely those which can be given in terms of a power series. They seem to have really wonderful properties. They're not the properties that the usual real value functions which are differentiable will have. A real value function is defined on R only, and differentiability at a point or a differentiability at a neighborhood is only one dimension. But once you talk about differentiability R and R, these functions pick up certain beautiful properties which those functions do not get. Okay? If I have a chance, I will start getting into giving you examples of that kind too. What happens? There are what are called real analytic functions. Real analytic functions are functions which can be which can have a power series expansion on the real line only, not on the whole complex plane. This is on the complex plane, not on the whole complex plane, in a disk around in Z0. But real analytic function is one real value functions, right? It's one which will allow a power series expansion around a point, but only on the number line. And they also do not have such beautiful properties as these functions have. Okay, but I can get excited only when I can prove to you some beautiful, useful theorems and analytic functions. So I'm quite anxious to get into that quickly, but I have some work to do. I have to show that these things are analytic, and analytic functions can be represented like this. Once I do that, I'm in a position to start talking about anything else. Sir?
Oh, it's good.
No.
Excellent.
All right, I urge you to read the book and try to do the exercises. I will also send some more exercises. Actually, what I'm giving you this course more for my own learning, frankly speaking. I knew some complex theory one time, but I'm not so good at it. I have to learn. So I'm learning a language. Okay. All right, guys.
Okay.
That's all
Thank
for
you.
you. And we meet tomorrow again at this time, 10:15. Is that okay, everybody?
I'm okay. I'm good.
Awesome. I'll send you the link. I will send you the note and the WhatsApp. And you all have a good day. Bye.
Yep. Thank you.
Thank you, sir.